Fusion is the process by which two light atomic nuclei combine to form a single, heavier nucleus. In doing so, they release a massive amount of energy. Without fusion, life as we know it wouldn't exist. Our own sun, and every star in the night sky, is powered by this very reaction. What makes fusion so fascinating is that it releases significantly more energy than nuclear fission, the reaction we currently use in nuclear power plants. This has led scientists and engineers to pursue fusion as the holy grail of clean energy for decades. But achieving fusion on Earth isn't easy. To make it happen, you need a state of matter called plasma, a superheated soup of positive ions and free electrons. But here's the kicker. This plasma has to reach temperatures over 100 million degrees Celsius. That's hotter than the core of the sun. At these extreme temperatures, keeping the plasma from melting the reactor walls becomes a monumental engineering challenge. That's why fusion devices rely on complex confinement methods, whether it's magnetic confinement like in the ITER project, inertial confinement using lasers, or Z-pinch methods. Despite decades of research and billions in funding, none have yet produced net energy gain. That is, more energy out than you put in. It's like having the smartest kid in class always just almost getting the answer right. Then there's cold fusion, one of the most controversial scientific claims ever made. Cold fusion first made headlines in 1989 when Martin Fleischmann and Stanley Pons announced that they had achieved fusion at room temperature using a simple setup, a platinum cathode submerged in heavy water, which contains deuterium, an isotope of hydrogen. They passed a current through the setup and claimed it produced both excess heat and neutrons, the byproducts of fusion. The idea was revolutionary. If true, it could mean cheap, clean, and limitless energy. But the issue? No one else could reliably replicate their results. And in science, reproducibility is everything. Even though the experiment resembles electrolysis, a well-understood process, the same heat and neutron results never showed up consistently. Still, the mystery lingers. Could there be a mechanism or reaction that we don't fully understand? Some scientists argue that while cold fusion as we currently envision it might not be viable, the experiments suggest there might be some anomalous behavior worth investigating. But here's the big caveat. Fusion at low temperatures and pressures faces enormous odds because of the Coulomb barrier, the repulsive force between positively charged nuclei. Overcoming that without immense energy is frankly improbable. Fast forward to today, and a new player enters the scene. Dr. Randell Mills and his company, Brilliant Light Power. His claim, fusion is not even what's happening. Instead, he proposes a completely different reaction involving something called Hydrinos, a hypothesized form of hydrogen with an electron in a lower-than-ground energy state. According to quantum mechanics, this shouldn't be possible. The ground state is the lowest energy level an electron can occupy. So, if hydrinos are real, it would challenge a century of established physics. In Dr. Mills's setup, liquid metal electrodes intersect in water and carry a high electric current. This interaction is said to ignite a plasma, releasing an intense burst of light. The reaction, he says, is driven by hydrogen atoms collapsing into this lower state, emitting massive amounts of energy. He claims the power density could reach up to 30 megawatts per square meter. That's huge, if accurate. The idea is to harvest this energy using thermophotovoltaic converters, which can convert high-temperature radiation directly into electricity. Dr. Mills has conducted several tests to support his theory. One is Raman spectroscopy, which involves shining a laser on a sample and analyzing the scattered light. He interprets the data as evidence of two-photon absorption from hydrinos. He also presents gas chromatography results, showing gas signatures that supposedly don't match any known substances, appearing faster than hydrogen or helium. Intriguing? Yes. Definitive? Not yet. These results need to be verified and repeated by independent laboratories to be considered credible. That's the sticking point, independent verification. If these mysterious results are real, other institutions should be able to detect them. Dr. Mills claims he's sending out samples for third-party testing. If they confirm his results, it could mark the beginning of a paradigm shift in physics. But until we see peer-reviewed publications or replication by neutral labs, skepticism is not only reasonable, it's essential. What's particularly interesting is how far the company has gone in prototyping devices to harness this reaction, from boilers to magneto-hydrodynamic systems, and now to the most famous, the SunCell. The SunCell has undergone many design iterations, all trying to manage the intense reaction from these liquid electrodes under massive electrical currents. The problem is containment. Pouring thousands of amps into a small volume of water and metal without destroying the chamber? That's a nightmare for any engineer. And even if they manage containment, there's the issue of converting the heat into usable power. TPV converters are promising and being actively researched for their potential efficiency. The best lab-grade TPV cells today handle about 24 kilowatts per square meter, and they operate best at around 2000 degrees Celsius. So even if the SunCell hits these temperatures, you'd still need a very large and very efficient TPV array to match the claimed 250 kilowatt output. So let's crunch that. Earlier SunCell versions needed around 1,500 amps for each injector, with a 40 kilowatt input. To get a true net energy gain, the TPV would need to operate at near-perfect efficiency, something that, honestly, hasn't been shown. The numbers just don't quite line up unless there's some unknown mechanism at play. And again, without third-party data, we just can't verify it. So far, much of what we have is based on internal reports and proprietary measurements. Dr. Mills is making bold interpretations of his data, no doubt about that. But science really moves forward when results can be independently tested. Until external labs confirm this is something new, whether that's Hydrinos or maybe some other unknown interaction, it, remains speculative. And honestly, that's okay. New ideas should absolutely be explored. But, as the saying goes, extraordinary claims require extraordinary evidence. Building a device that delivers energy from a 1-inch wide plasma reaction without melting itself? Another point of concern is that some early designs, like the boiler variants, never showed actual power output. If those had worked, they'd be the simplest proof of concept, right? So why haven't we seen a working demo that produces sustained and measurable power? If they exist, showing them would go a long way toward proving this isn't just cold fusion 2.0. Maybe this isn't fusion or Hydrino formation. Maybe it's something else entirely that we don't yet understand. And that's really the central takeaway here. While cold fusion and Hydrino theory may sound like fringe science, they both raise important questions. Could there be energy pathways we haven't yet discovered? Could our understanding of quantum states evolve? Possibly. But we have to remain grounded in the scientific method. Observe, test, replicate. Until then, both cold fusion and the SunCell's Hydrino reaction are fascinating, but unproven. That doesn't mean they should be ignored, but they should definitely be approached with a healthy dose of skepticism. So where does this leave us? Somewhere between curiosity and caution. Whether it's the high-temperature dreams of hot fusion, the elusive promises of cold fusion, or the radical ideas behind Hydrino theory, the quest for breakthrough energy technologies continues. We're talking about the possibility of changing the world's energy landscape forever. But we can't do that without scientific rigor. That means peer review, replication, and transparency. Until we see that, we should keep asking questions and pushing for real answers. If you found this breakdown interesting or have your own thoughts on fusion, Hydrinos, or the SunCell, let me know in the comments. Do you think this could be real, or just another energy unicorn? Don't forget to like the video if you learned something new, and subscribe for more deep dives into science and tech.